Good afternoon, everyone. Thank you so much for joining. First of all, I would like to start with thanking SNIA. SNIA has been persistent in positioning me in the best time slot possible always. Last year, they positioned me right after lunch, and right now, I'm the only thing between drinks and dinner, and all you guys after the onslaught of the entire afternoon. So thank you, SNIA, for making people not like me much. So last year I spoke about the entire AI data pipeline of right from pre-training to data ingestion, pre-training, inference, downstream tasks, and how vector databases impact the underlying hardware infrastructure. It be compute, network, storage, and at scale, how does it impact each of those? This year, I will talk about something very different. I'll talk about why, when you're trying to train or have these large clusters being built out at data-centric scale, why do you need to bake in resiliency? Why do you need to make training more flexible? Why do you make it more efficient? And why does it, and we are trying to build all across the entire, like at planet scale. So what does it mean that when errors happen or when failures happen, how do you recover from those failures? This talk is about how do you do it efficiently, understanding your system resource limitations, and also the point that you need to make it optimized for the entire end-to-end platform. So please bear with me as I go forward with it. I hope to finish early. There's only two things which can stop me. Either I run out of slides or my battery dies out. You may expect the second one to be first. So thank you so much. So today it's a highly simplistic talk. First, as always, I try to create content so that it's digestible by all. So I'll just go through some systems like reliability 101s. I won't go into a lot of details because last year I've covered those internal details. So you can refer to my last year's slides. And I'll talk about what does infrastructure mean and how does reliability impact your training efficiency. These are two different orthogonal aspects. How does these two marry each other? And then I'll talk about, hey, there's a big problem that I'm talking about adding fault tolerance and resiliency to manage failures, right? But managing failures themselves become that expensive that when do you do training? So we'll talk about how we quantify what I call as the fault tolerance tax. And then we will discuss upon a specialized use case of resource rebalancing, which is getting very common in data centers now. And our work on top of like vanilla deep speed universal checkpointing, that's a collaboration with UIUC with Professor Minchazak. And then I'll conclude the talk and we will talk about the various community aspects of what needs to be done in order to make systems like your fault tolerance and your systems work together for developing these AI training systems at planet scale. So let me go forward with my first slide. So this slide will talk about what does some terms which I'll use throughout the presentation on infrastructure reliability. Please refer to my last year's talk on what applications mean, how AI impacts each of those components. I'll not go into those details in this talk. So let me go forward with few terms now. SNIA has always taught me from the core, so I wanted to make it that everyone understands. Please bear with me who know about these terms. So today in the morning, Jay talked about good put. So what is the training good put? It is the actual amount of compute throughput you spend per unit time. That is the actual amount of progress you make. That is defined by tokens per second. So however, this is a great metric, but for infrastructure providers, this may not include all the details about idle time, how much time your GPU is staying idle, what it's doing other than training, so it doesn't capture all those metrics. So there are other metrics which do that. One of them is model flop utilization, which is the total amount of flops a model utilizes for training than what the GPU providers or peak hardware flops which are available. The next one is more interesting, rather. So this is called the mean time between failures. What does this actually mean? In these large-scale systems, or even for smaller systems, there are millions and billions of components, and each of them have a failure domain. And when they work together, the failure domain just goes to a different level. So what mean time between failures captures is that how much is the average time between two failures which would be there in a system deployed at that scale, at a particular scale. So this is a very important metric because it tells you that, hey, how much amount of resiliency you need to bake into a system? How much is required? How much recovery do you need to do? We'll talk about how recovery relates to I/O in my next couple of slides. This actually impacts a lot of storage world, and about all the use cases you have heard today, it impacts all of them, nearly all of them. So please remember this term as mean time between failures, or MTBF. And the final one is effective training time ratio, which is the actual time you are doing training than, it's a ratio. So it's actually the actual time you're doing training, backward, forward passes versus the total time. This eventually is a data-centric metric, which tells you how efficiently you can train these models. It be large foundation models, small foundation models, whatever. So this is the metric which most of the data-centric infrastructure people follow. So in short, to achieve high training output, you have to, and maximizing the model flop utilization is a key goal. And the basis of it is to make ETTR, or effective training time ratio, to optimal. It's a mathematical function though. And this is a very real challenge. However, now I would like to discuss upon, how do any of this mean for failures? What does failure have to do with training efficiency? Why is that? How does failure actually impact your training efficiency? So my next slide talks about that. It talks about how reliability and training efficiency at scale really matter. I'll bring upon a projection of the mean time between failures versus the number of accelerators deployed for an AI training system. This is not actually, this doesn't represent any single accelerator. It can be any number of accelerators, but it is across millions and billions of these components which work together in a data center hierarchy. What this clearly shows is that with the number of accelerators you increase, your rate of failure increases. Think about it. A node would fail you're doing a job only within a node, it may not even fail in years. If you're doing at rack scale, it may about a couple of hundreds of GPUs, then in 3 to 6 months, you would see a couple of failures. In cluster scale, it's around less than a month or 3. When you go into data center scale, all these colossal big GPU farms being created, you would see failures in the order of minutes. And just when you project it into 1 million GPUs, which is not very distant or far away. We have all seen all the tweets across that a 1 million GPU system is not that far away. You will have failures within minutes. However, the bigger challenge is that when you have these kinds of failures, then how do you recover from these failures? Because you need to go back in time and then you need to start your training again. So this is the bigger challenge. So with this growing scale of these AI deployments, the mean time between failures decreases dramatically. Therefore, resiliency is the core for achieving high training efficiency and for increasing the training output. The reason is that now you need to be always resilient, that there will be a failure all the time, and you need to recover from that failure. How do you do that without impacting your training efficiency? How do you quantify that? For that, the next slide really quantifies and tells you what eventually are some mechanisms through which these systems employ in order to build resiliency. The next slide, all of you, I'm 100% sure you would have heard more than maybe 50 times today. So from a previous slide, we understand that, hey, fault tolerance, resiliency, recovery, all of them are important. There will be a failure all the time, and you need mechanisms to recover from that failure. But what is that mechanism? And I'm sure you've heard about it, or maybe not. So that's storage community's poster AI use case, that is checkpointing. Like, I don't want to go into details of what checkpointing, that has been discussed in detail in my previous talk. However, what checkpointing does is that from this simple figure, is that it's a critical fault tolerance mechanism to persist your training snapshots periodically to either persistent store or any form of reliable media so that you can roll back in the event of failure. These red box show your training steps. The yellows are when you do checkpointing. Of course, you can overlap that. There are many techniques, but for simplicity, let's keep it like that. During failure, you need to go back to the previous checkpoint, and that's how you recover. Very simple, right? So this is not just used for pre-training, but for hardware refreshes, resource rebalancing, and post-training, and other tasks as well. Checkpoints are used more than just recovery. So as you would have realized from my previous slide, that with scale, your MTBF is going low in order of minutes. That means that you have to do more checkpointing. More checkpointing means that you will spend more cycles, like times, than you can do training. So your ETTR goes down, and you are imposing heavy data center tax. I've spoken about data center tax last year about how this impacts not only your front-end network, but your NICs deployed, the front-end network, your back-end network. It creates a havoc. So that's what it really does. But we need to quantify this in order to develop optimal solutions. For infrastructure providers, fault tolerance tax is pretty important. And when you say fault tolerance tax, the major contributor to that is checkpointing. Let's just revisit the figure I showed earlier. Here, the reds are what you want to do, the training. The yellows are that you want to minimize the impact, that is the checkpointing. And then I'll talk about the blues and the greens later. So the reds are that you are trying to make progress over training. This is good. You should have more of those. However, you incur some kind of a tax to save the checkpoint. And then when a failure happens, eventually one failure or multiple failures, you are losing that much job all the time. So we just use this iteration, we call it the iteration loss factor. And then once that iterations are lost and you have a failure, you need to roll back to a previous checkpoint. But you need to recover from the failure first. You need to detect and recover the failure first. So that's we call as the recovery tax. And next is that you need to load the checkpoint, you need to deserialize the checkpoint, and we call it the checkpoint load tax. So the fault tolerance overhead can be easily, this has more mathematics behind it, but this can be easily represented as a summation of all these factors. That is, this is the amount of time or performance or cost you are spending to manage your failures. And this can get very significant. Sometimes managing failures itself becomes more challenging than actual failures themselves, and they contribute more. And we'll show evidences for that. So the effective training time ratio, the higher the better, but the fault tolerance, it clearly shows that more the fault tolerance, lesser is your ETTR. So infrastructure providers have now a choice between each of these components, what to reduce or what is more significant for them. And achieving this optimal ETTR is a real challenge for data centers. Without optimizations of each of these components, systems may spend more time in managing failures than actual training itself. However, ETTR and the fault tolerance overhead, there is always a trade-off between what you need, what your customers need, and how you can deliver it, and what the system can actually deliver, right? So you do excessive checkpoints, the T-save gets increased, and your data center tax increases on both compute, network, and storage. But you do infrequent checkpoints, now you have to recover more. So your iteration loss are much more than what you can afford to. So that's always a balance. So you need to, your reliability mechanisms need to have the optimal ETTR, and which should balance both performance, scalability, and cost effectiveness for your infrastructure and for your customers' needs. Now, going forward to what is being done. So what is, like, just 1 minute slide. What is checkpointing? You all heard about what really is on top, that it is a rollback mechanism. Last year, I quantified how much checkpointing, the size of checkpointing grows with the number of parameters. Now that can change, the graph can go up and down, but that's the trend. However, what checkpointing really does, there are two major steps. One is the serialization part, where from your GPU memory, you're trying to collect the weights, the optimizer states, and the CPU states and the metadata into a tensor compatible structure, which can be either a file or an object, and then you have to persist that file or object over the network. This can change with the parallelism and the framework deployed. I will not go over the details today. Please refer to my previous talk on this. So this trend is going up, and the frequency of checkpoints will also go up. Because there can be other mechanisms, but for now, based on the GPU, CPU, remote storage world, this pattern is consistent. So traditionally, how checkpoint is being done is that you have these training steps. In between, you are doing checkpointing. Then after you copy from GPU to CPU memory, you do the IO serialization, and then you are doing training. This is done by the main GPU or the training thread, and you are stalled. This is simple, but introduces stalls. The GPU underutilization is there. Then there's cost involved. It's bursty for both the front-end NICs and the back-end, not the front-end NICs as well as for the storage NICs, and it has strict SLAs. So this synchronous checkpointing, or the traditional way, poses unique throughput, latency, and network challenges, and it can easily oversubscribe your system infrastructure, storage infrastructure, and the GPUs have to stall to resume training. However, as we know, that when there's a problem, the community comes together and tries to address it. So there has been optimizations on top of it. The first optimization was that, hey, you have this main training thread. Why don't you decouple IO from the main thread? And that's what asynchronous checkpointing really did, is that you have a separate thread. One thread, once you copy the checkpoint from a GPU to the host memory, the GPU can start training, and your IO persistent thread would do the IO serialization. That's called asynchronous checkpointing as per the PyTorch distributed checkpointing terms. However, there are more caveats to it. Now, you are trying to overlap communication with computation. You want to alleviate the main GPU thread. You want to use the IO thread to do this. It really reduces the pressure in a lab. Also, we figured out that from the storage system by buffering it on the host memory, but your host memory is also limited. And is this truly asynchronous? All of you who are storage developers really know what asynchronous is, right? So on IO verbs, this may not be asynchronous. So the main challenge here is that though the current implementation has optimized it to one level, but you are still consuming a lot of host resources. Your CPU memory is being oversubscribed. Now people would come about, hey, why not shift it to local NVMe? People do that all the time, but there are persistent local NVMe may increase the fault domains. Maybe not. So there is a need for advanced memory and storage tiering, right from how you store from the CPU or the host, from HBM to either the host memory or local NVMe to a parallel file system and to an object system. How do you do that tiering to mask the IO and computational latency while making it truly asynchronous? This is a challenge. People who have developed storage protocols know how difficult it is to develop asynchronous IOs. And actually developing it is easier, but deploying it is even 10 miles ahead. So that's on the saving part. There has been a lot of emphasis on saving checkpoints and writing of checkpoints. Like throughout last year, everyone has been talking about it. But the bigger challenge is not saving checkpoints. The bigger challenge is loading checkpoints. Very few people talk about it. And this is what really impacts your training. Writing can be made asynchronous. But how do you know when an error would happen? So what does loading checkpoint really mean? Is that from your persistent storage, you have to take all those checkpoint files as soon as possible and load it to a GPU, and a correct checkpoint file has to be loaded to one GPU. For writing, a rank can write only one checkpoint file, but for reading to resume training, all GPUs have to read the checkpoint files to their particular HBM. This is a very big challenge because this can destabilize both your storage infrastructure and your GPU node infrastructure. The reason is that the number of connections required to load each of these checkpoints to the GPU is massive. There's a hell lot of redundancy. What really, let's now go step back and think, what does this checkpointing really, loading of checkpoint really means? It has two parts. One is raw reading of the file or object from your persistent store. It can be file system, it can be a parallel file system, it can be an object storage system or a tier of that, but loading it to a GPU server node and then deserializing it. People who have really developed this, like have hands-on practice would know how much impact deserialization has. It has more impact than actual loading in some few cases. What does deserialization mean is that you have loaded your checkpoint file, but you need to first unpickle it, or rather deserialize it to a format that is amenable for the GPU to read. So you need to read the metadata, you need to, from the CPU structure, you need to move the data to a GPU amenable structure to the HBM. This is a very big challenge. And as I already stated, that to resume training, all GPUs should read the data simultaneously. It has a massive I/O amplification compared to writing of checkpoints. And this should be given more emphasis. Just not for resume training, but it's also used for downstream tasks, for post-training, for inference, whatsoever. So loading of checkpoint is mission critical. This leads to real bottlenecks in the GPU storage hierarchy because it has high throughput requirements, it has tight latency, you will have network contentions, there will be a redundancy over the network, you will have congestions, and of course, on top of it, nowadays systems are all multi-tenant. So that's the challenge here. Now, of course, when I talk about a challenge, there are optimizations. So the next part is this is what we talked about right now, right? However, there have been optimizations across the cloud community as well as other communities where they understand that, hey, we have this massive storage infrastructure, but it is limited by the number of connections it can have to the front-end network of the dense GPU clusters. So people thought about why not use the back-end GPU to GPU communication and faster network to load the checkpoints. How is that even possible? It is possible because of, let's discuss the first principle. The first principle is that these checkpoints, not the entire checkpoint needs to be loaded on one GPU. There are shards of the checkpoints which are needed. Moreover, the second point is that, forget about the shards right now, but there's also a lot of redundancy. Across a model replica, you would have the same copies being transmitted. So why not use the back-end GPU to GPU faster network to do all this? So what really people have come up with is that, use the compute network for checkpoint loading. What this really means is that you designate few nodes as coordinator nodes and few nodes as receiver nodes. What the coordinator nodes really do is that they load the base checkpoints from the storage layer, from the object storage, let's call it the object storage layer, and it reads the checkpoint. It tries to create those, whatever shard, it tries to deserialize it, and whatever shards are required, it tries to broadcast it over the backend network, that is the GPU, and make use of the GPU-GPU communication. What this really helps in doing is that now you are reducing the number of network transfers, point one. Point two is that you are using the fast backend network. The third point is that you are balancing both The storage infrastructure, now it doesn't have to deal with all these thousands and thousands of connections. It just has to deal with what it can do best. Few connections, sequential I/O. That's it. So you can, and these are the kind of techniques which are used at scale, and the GPU storage data path optimization need to be topology aware. This is one example, but you have different construction, different topologies. So the infrastructure is actually need to be built around how your needs are, what kind of models you're running, what kind of like I/O requirements are there, and how you can use all the networks available to you in order to have a robust infrastructure. Now, I would like to discuss on a very different challenge. Like we talked about all kinds of fault tolerance. We talked about all kinds of efficiencies, right? There is one problem that now recovery for all those, there are optimizations being built in the community. However, what about elasticity? What I mean by resource elasticity is that suppose your number of GPUs really change, or your type or your parallelism changes. How do you use the same checkpoints? How do you recover from failures? That is the major challenge. I'll go into details in the next couple of minutes. So resource rebalancing or change of GPU shape is very common in data centers. Not very often talked about, but it is extremely common. What it really means is that suppose you're doing pre-training. I'm just giving one example. You're pre-training with 8 GPUs with a particular parallelism configuration. This divides your model shards, your weights, your optimizer states in a particular format. They store the checkpoints based on those formats. However, at a particular point of time, if you have errors or failures, as we see it, they're more common, and you change either the number of GPUs or you change the parallelism. Parallelism can be changed for multiple formats. Sometimes the loss goes into such a, the large channel loss goes into such a like pattern that you need to reconfigure your parallelism. So in that case, how do you recover? How do you resume training? Look into these two figures. You will see oh sorry, it's very difficult for you guys to see, I guess. So you would see the different color patterns. So how do you, these color patterns represent that the layers and the model information. So your initial checkpoints are highly integrated or tightly coupled with your hardware configuration and your parallelism. We all know that. But how do you convert that into something like this, and that too on the fly? Your recovery time will go off the roof. This is a major challenge. And this is not just used for training, but also think about it. You have some checkpoints. Now you are doing some post-training tasks like supervised fine-tuning or reinforcement learning, where you have a requirement of a lower number of GPUs. Then how do you do this in an online fashion that, hey, I have checkpoints for this particular parallelism. Now I have lesser number of GPUs with different parallelism. Then how do I load those checkpoints into these downward tasks, and that too in an online fashion? These are the use cases, that is for training resuming, for post-training, and for inference. These are very common in data centers. This is the I/O problem. I'll talk about it next. So this impacts both recovery. When I say recovery, that you have an initial initial parallelism, then you have a target parallelism. How do you make the same checkpoint files work for both? And what is the mechanism to resume this kind of operation? And then you have to load that particular checkpoint. Existing frameworks do provide highly limited support for reconfigured parallelism. This is growing, but it is highly limited, and not all kinds of parallelism are supported. And it is highly inefficient today. It is done offline with handwritten scripts and with human intervention. This increases your recovery time, and you spend more time in recovery than doing actual training or the actual work. So these distributed points are tightly coupled to initial parallelism, and which results in the GPU staying idle and not doing work. And the resharding, it limits the adaptability to these resource elasticity. So with this, we actually, the problem statement, because of the problem statement, there is an existing work known as deep speed universal checkpointing. We work with the co-creators of deep speed universal checkpointing to address this challenge over vanilla version of it and optimize it further. That is with Dr. Minjia Zhang from UIUC, who's the co-creator of deep speed UCP, and his PhD student Junkan and Shinyu. And we develop on top of vanilla deep speed universal checkpointing to support it on AMD GPUs and how we can support all this, creating a resilient and efficient checkpointing. However, the bigger goal is that how do you make it resource efficient? How do you make it aware of the storage infrastructure, as well as change the algorithms or how you access data from the entire stack optimization. So what is universal checkpointing? It was developed as a part of DeepSpeed, which supports multiple commercial models, as you can see from the screen. What it really does is that it automates this reconfiguration or this resharding of checkpoints. Given any any combination of these parallelism in target or in source, what it does is that it automatically it defines a language and it supports various frameworks, and it automatically matches the pattern to your target configuration and changes your source checkpoints to the destination. So how it really works is that, let's have a 100K view, bird's eye view on it. Suppose you are saving checkpoints periodically. This is all your DCP, PyTorch DCP checkpoints. What it really do is that you cannot load that checkpoint if your GPU configuration or GPU shape changes. So what UCP does is that you are tightly coupled with the parallelism. So it tries to first decouple the parallelism. What it really means is that from your source checkpoints, which is of initial configuration, you read all these checkpoint files, these massive checkpoint files to your through the front-end network, from your storage network to your front-end network to your GPUs, then you CPUs or GPUs, and then what you do is that each of those contain the parameter information. You extract that information, write large number of small files. I know you guys would love this problem. Write large number of small files, then read those files and recreate the each parameter files, that is the weight, momentum, and variance. Now you are writing all these medium-sized files again back to storage, and what it eventually does is that, hey, now someone tells me that I need to change to this parallelism. The language automatically detects that, and based on the pattern matching, it tries to read from these checkpoints known as atomic checkpoints, that is per parameter checkpoints, and converts it into target parallelism and then loads it to the particular GPU. This is all automated. However, we wanted to test it out. So about accuracy, because irrespective of whatever you do, if your accuracy is lost, then the recovery doesn't mean anything. What we did is an experiment. First, the blue shows you that we did experiments with like 32 instinct GPUs with a initial parallelism. It clearly shows the loss function. Then at our next experiment, what we did is that in between the experiment at a particular epoch, we injected a failure. The system goes down, we start UCP, and the orange detects really shows the loss function. This shows that the blue and the orange are very close together. That means that the accuracy loss is minimal. So UCP is a good technique for failure recovery with resource rebalancing, and which doesn't compromise the training accuracy. However, as most of you who may know me, I always do under the hood analysis, and we worked with the PhD students with our collaborators at UIUC, and we looked into what goes behind the scenes. Here, on a figure on your left, we compare the native PyTorch distributed checkpointing with UCP. You would see that UCP has to do extra work. That's why it's taking extra latency, extra time hit across different models, different parallelism. There are more results, but we just wanted to show two. The red shows how much time it needs to convert from an initial parallelism to a target parallelism, and the blue shows how much time it takes to load. So conversion and your loading latency. This is apples to orange comparison because DCP doesn't have to do that extra work. It doesn't support reconfiguration. However, UCP needs to do that. And that's the reason why you would see that UCP, this kind of fault-tolerant mechanism incurs more cost. It has to do extra work because it has to do the decoupling of the parallelism. It has to load all those files again. It has to load it to the target parallelism and do whatsoever. But we wanted to look more ahead into the I/O. This is an I/O conference. So you need to know what goes behind the scene. We observed that UCP's I/O volume is 4 times that of DCP due to this kind of reconfiguration. And this is required for different kinds of patterns. Why? We went ahead. I talked about multiple stages of decoupling of the parallelism. And we profile the torch.load and save calls. Now you can clearly see what I spoke in my previous slide and now. The blues show that you are loading these massive, all these checkpoint files to the GPU nodes from remote storage. Then these reds show you, These reds, what you do is that you read them, create those small files per parameter, store it back to, let's say, a high-performance NVMe storage or a remote storage or an object storage. There is a lot of packing, unpacking, serialization and deserialization, lot of rsyncs, lots of open and close calls, and then you read them back again. These red dots really show that you read all those smaller files again to create the per parameter atomic checkpoints. This is a very expensive operation. And we all here know about the large number of small file problems, the metadata associated to it, and how serialization and deserialization really causes all these issues. Apart from just the latency, this consumes a lot of GPU node host resource consumption because of temporary file creation. And this is not consistent. It changes with time. It changes with the phase of your application. It changes with the parallelism you are trying to target. It also changes with the model you are running. You need to be adaptive to all these factors. And this finally leads to the GPU storage remote bandwidth underutilization because of serialization and deserialization impact. And there is the in-node parallelism, which is not really exploited. So you need to do extra work, we know that. However, there are two things here. First of all, the methodology needs to change. Second, you need to know what is your actual underlying infrastructure, what is your topology, where does the storage node sit, how many number of connections, what is the limitation of your GPU nodes, what are the workloads. It's a dynamically changing pattern. So we redesigned this. What we really did is that we developed a solution from ground up, thinking about how a naive I/O problem can be solved, given that these are the characteristics of it. We did infrastructure-aware optimizations. We know that your storage infrastructure, depending on where you sit, will change all the time. You will have different kinds of medias, so you need to be aware of the throughput. You need to know the backend, whether it's a file or object backend. You need to know how the cluster or your front-end networks are designed or are actually located. What is the current workload of those particular nodes? You need to know what kind of memory you have on a GPU node, what kind of HBM or your host memory you have, and how much leverage do you have. Because you don't want to oversubscribe either the front-end network or the storage infrastructure, because with congestion comes the associated domino effect. So you will need to be agnostic of the network bandwidth. Then we did inter and intranode optimizations. As I already spoke about that, you need to know how much host resource or a budget you have. You need to know your dynamic workload pattern. Then we also changed the algorithm that we showed you that, hey, you have two steps, right? Decoupling parallelism and then loading and converting. How can you merge them in a step that you eliminate the intermediate files which are being created? Because with intermediate files, it's not only the large number of small file problems, it also is a metadata problem. Metadata is a bigger, I'm a big proponent of the fact that metadata is a bigger problem than data itself. And that's where we did metadata optimizations. We understand that how these objects are laid out or files are laid out in a remote storage environment. We know how the metadata, what kind of information does the checkpoint file metadata contain. We use that, and we use advanced optimizations such as memory mapping and offset-based dynamic loading. This is a newer construct where you use both memory mapping, you use the metadata information of where all these parameters are stored. First, you create a map in memory, then you use memory mapping, and you eventually load all the data from remote storage as if you are reading just offsets. You're not reading files, you're just reading offset. Think about a bin file, you know what all information you need, and you're just pointing to a range of offset. This eliminated the need for temporary file creation. And we reduced as this graph really shows you that we reduced the overhead or the burdens by 1.5x to just load the checkpoint and recovery by 2x. And this shows that we are getting closer to DCP performance, that is traditional PyTorch distributed checkpoint performance. As you can see from the first and the third legend, that we are getting very close. This is simply because of all these optimizations which reduce the traffic by 2x. It reduces your GPU host resource consumption, the IO traffic, the amount of IO traffic you would create, the redundancies across the network. It increases your storage bandwidth utilization, which actually result into these lower latencies. So this is one use case. This is one feature set. And it clearly shows that all these fault tolerance mechanisms need to be created, keeping in mind both the GPU node constructions and the storage infrastructure. And if you could manage them and create a scenario where you are reading files as they were designed to read, then you could also improve your training output and increase your effective training time ratio by just doing what natively systems are designed to do. So I would like to conclude now. First of all, the trend is really clear that with scale and the size of AI deployments, failures will be inevitable. You need to assume that failures will happen all the time. You need to develop or build systems which have resiliency inbuilt. And as the MTBF goes low, you need to have those mechanisms that, hey, I cannot afford to lose my training efficiency because I'm managing failures. You need to build systems from scratch. You need to build a robust and scalable and cost-effective mechanism, which should be the core for developing all these techniques for achieving higher training output. Resource rebalancing is becoming critical. It's becoming common in the AI lifecycle. And that's the reason why you need to make not just AI training fault tolerant, but it needs to be flexible, it needs to be efficient, it needs to be elastic to changing resource patterns, and it needs to be adaptable to different infrastructures what you have. One size doesn't fit all. So you need to have it adaptable. My previous experiments did show you that if you can manage all these different varying factors, like different orthogonal factors, then you may be able to achieve better efficiency depending on the infrastructure you have. So UCP seems to be a promising direction. However, it needs full stack optimization. So are other solutions which we need to create as a community, which need to know about your GPU node. It needs to know about your network. It needs to know your front-end network, your back-end network. It also needs to be aware of the dynamic changing patterns. And it also needs to know what kind of storage infrastructure it is dealing with. And with this, I would like to conclude my talk by saying that as a community, we need to build such recovery mechanisms which strike the correct balance of performance, scalability, and cost of effectiveness that is how we will be able to fully harness the potentials of GPU-accelerated AI computing. Thank you so much. If you have any questions, we have around 5 minutes for that. Yes, Bill. So you're showing it having to reload all checkpoints for all nodes. So, Bill, your question is that you need to load all checkpoints to all GPUs in the event of a failure, right? Yes. So the reason is it's not that you're tainting all your GPUs. It's just that you cannot proceed to the next step, or you cannot proceed to the next step till the time all your GPUs are in the same state. So your GPUs are idle, they need to, and they have to, and it's not that they work in tandem because there's communication, there's collective communication between them, so they need to work in tandem to even progress with training. So you need to load all the checkpoints in order to even proceed for the next step. Did that answer your question? Okay, we always talk. Yeah, please go ahead. Oh. Okay, so let me answer that part-wise, right? Your question is that, hey, we spoke about an advanced optimization where not all GPUs initiate the I/O for checkpoints, right? And you have the coordinator nodes and you have the receiver nodes, which the coordinator shifts the broadcast over collectives to the receiver nodes, right? So to answer your question, it's not the same number of I/Os. It is significantly less, because now think about a scenario where you have model replicas. So in that case, nearly the entire, all the checkpoints are nearly the same for a particular set of GPUs. So that is answered, right? Okay, so yeah, please go ahead. Yeah. Yeah. So, I should have gone over it today. However, in my previous talks, there is a barrier. And at either particular epochs, all GPUs need to persist their state either to a lead GPU who tries to consolidate the checkpoint and store it in storage, and it is all, they talk over the collective networks to, after the backward pass, they collect the state, and till the time one particular node, responsible node, doesn't push the I/O, your training doesn't proceed. So it is defined at particular epochs or steps. Epoch is, yeah, you can call it time or steps, training steps. Dump your state. Yeah. Yes. So those things are built into PyTorch. You have a question?
Yes, consistent snapshots were a problem, a major problem.
So there is, this is actually a very interesting question. I think this is probably the best question. So there is, yeah, one of the best questions. So it is, purely it is not really atomic, you are losing out information. So, but at a particular slice of time, you are consistent across everyone. It is not that you think about it as eventual consistency. So that's how I would answer it.
Consistency in raw data.
Yes.
Consistency in
Yes.
So let me ask a second question.
Yes.
Illuminate it. That is this problem related to the firing squad problem?
What is that problem?
The firing squad problem is a distributed algorithm where all of the things are taken a snapshot of the event.
Actually, my time's up. Let's discuss this in a call right now. But they are flagging me for a time's up right now. So I'll try to skip that. Thank you.